Welcome back to the Copper Isolation Lab. Today we're going to be focused on figuring out the data and how to get the answers that we want from the data. And in order to do that, we're going to have to look at the stoichiometry as well as the reactions. Now, as you remember, the reactions that you carried out first were having the first reaction that you carried out was dissolving the ores in concentrated nitric acid. And when we did this, this severed the ionic bond between the copper 2+ and the carbonate. Or if we had iron or zinc carbonate in there as well, it also severed those so that they became the metallic cations. So you had metallic cations in solution at the end of this step, and you had Gang, which was stuff that doesn't dissolve in anything, okay? So then you had a filter. Once you filtered it, you took this copper and other metal 2+ solutions, and you added ammonia to it. And the ammonia made it very basic, and it took the copper 2+ to copper 2 hydroxide, and it took the other metals to their hydroxides as well. Then quite a bit of additional ammonia was added to it, and that ammonia reacted only with the copper 2 hydroxide to give this tetramine complex, this copper tetramine complex, which we had in aqueous solution. The amine did not dissolve or react with the iron hydroxide or any of the others, okay? There was no reaction. So we had a whole bunch of solids of the various metal hydroxides that were left from this step that were still solid. So again, we filtered. And after this step, we had done a second filtration, and now we were left with just the copper tetramine complex, we hoped, and the remaining nitric acid, and the leftover base that we had in there. At this point, we dissolved the copper tetra. We had filtered it off. We had gotten our first mass. So this was going to be our starting mass for our stoichiometry. This was the first nice clean substance we had. So starting mass for stoichiometry. Right here, the copper tetramine. So we massed it, then we dissolved it in water, and then we made it a little basic, so it went back to that copper 2 hydroxide, but not with ammonia, not enough so that it took the ammonia, made the tetramine again. The next step after that, we filtered and dried this so that it was this gooey, gummy, pressed toothpaste-like color. And we took that and then we drizzled some warm sulfuric acid over it. And that reaction gave us copper 2 sulfate pentahydrate. And this was where we stopped last week. We had the mother liquor for that, and we let it sit all week long so that we had some really nice crystals that we could mass and do stoichiometry with. So this is another stoichiometry point. There's a stoichiometry point. Here's a stoichiometry point. And of course, our last copper is a stoichiometry point. So what we had to do this week was we had to take that copper 2 sulfate pentahydrate, dissolve it in water so that we release the copper 2+ ions, and then react them with zinc so that we reduced the copper 2+ to copper plus, what we wanted, and our zinc was oxidized to zinc 2+. Now this we had to do using the competing reactions with zinc and sulfuric acid so that we wouldn't end up getting pennies, we wouldn't end up plating out our copper on a solid zinc base. Foundation. All right, so this is what we have here. We just traced back through really quickly through what we were doing. Now I'd like us to also look really quickly at the other thing we're going to need for stoichiometry, which is our molar ratios. Like I said, we are starting here with our stoichiometry, with this tetraamine complex. And we'll notice there's no stoichiometric coefficient in front, which means 1. And over here, it's 1 copper tetraamine complex yields 1 copper 2+ ion. 1 copper 2+ ion yields 1 copper 2 hydroxide. 1 copper 2 hydroxide yields 1 copper 2 sulfate pentahydrate. And 1 copper sulfate gives us 1 copper. So our molar ratios all the way through are 1 to 1, which makes life so much simpler. Okay, so let's go ahead and start working with some of the data that we've got. We went through and did this and got ourselves some data, and we're going to play with it. See if we can figure out what we're doing. So the data's over here. I'm trying to get to my calculation sheet. There we are. The data's over here, and you can see that our very first mass that we took was on the top loader, and it was a very rough mass of the ore. We didn't need that mass anything more than an approximate because that's not what our stoichiometry is based on. Our stoichiometry is based on this, which we're going to call copper 2+. No, we're not. Crap, I can't do that, I guess. Which we're going to call copper number 1. Okay? And that's a typo. Now, our empty beaker was 129.5010 and our grams, and our beaker with our copper in it was 134.5010 grams as well. Now remember, this is not the same substance, okay? This is the ore, and this is an actual compound. So when we subtract these two, we found that we had 5 grams of the copper tetraamine complex. And our first calculation question was, how many moles is it, and how much copper 2-sulfate pentahydrate can we get from it? So coming over here, we took our our 5.0000 grams, and I'm going to call it again copper number 1 because I don't want to write that whole thing, times 1 mole. We're doing our stoichiometry, going to the moles. Copper number 1 mole per 255.68 grams. Now we're going to stop there because we needed to fill this in. And that we did. It went right over into this spot. Now we were looking for the theoretical yield of copper sulfate pentahydrate. So we had to go further than this. This is where we are right now. So now we take this, we're going from moles 2 moles, right? So 0.019556 moles of copper number 1 times 1 mole of, let's call this one copper sulfate pentahydrate copper number 2 per 1 mole of copper number 1 again. Our units cancel and we end up with 0.019556 moles of copper 2 sulfate pentahydrate. But it does say it wants the theoretical yield in grams. So we have one more step to go through, and that is going to be converting this 0.0195556 moles back into grams using the molar mass of copper 2 sulfate pentahydrate. Our moles cancel, and we end up with we end up with 0.48330 as our 4.8830, there we go, as our grams of copper number 2, of our copper 2 sulfate pentahydrate. That's the theoretical yield. Okay? Now, what did I uncover here? Well, these were 2 other readings I took later on at the beginning of this week when I had my beaker that had my that was nice and dry and empty, and I put my copper sulfate pentahydrate crystals into it, and when I weighed them, I found that I had just that many grams that I actually got. That's my actual yield. All it was the difference between these two. So my actual yield so the actual yield for this was the difference between 104.8621 and 102.2435, or 2.6186 grams of copper 2 sulfate pentahydrate. Now, when we think back, we remember our percent yield is equal to the actual yield divided by the theoretical yield times 100%. So that's what we have to do next. We have our actual yield, we have our theoretical yield. So our percent yield is 2.6186 grams divided by 4.8830 grams times 100%. And that was equal to 53.626%. All right. So we have managed to fill in the whole top half of this chart, just with a few simple calculations. Okay, so we're going to continue on now. At this point, you cleaned off your crystals, you dried them, you masked them, and then you redissolved them in the water. You redissolved them in water, and then you had your copper 2+. This released the copper 2+, and you ended up with a copper 2+ solution, blue, okay? And what you wanted was copper. That's where we're headed in all of this. And so you had to add some zinc and sulfuric acid. And what the zinc did, of course, was to reduce the copper, just like we've shown a couple times already this lab. The zinc reduced the copper to copper metal, and you ended up with zinc 2+. The point again of the sulfuric acid was to keep that, to provide a competing reaction for the zinc so that the copper would not plate out on it and ruin the purity of the copper. All right. So at this point, we've got this blue solution sitting around, and we have to make it get to copper, because all of the rest of our questions from here on out are dealing with copper. So we got to get it there. How are we going to get it there? Well, your instructions said to put in, twice the number of moles of zinc that you had of copper 2 sulfate. Twice the number of moles of zinc that you had of copper 2 sulfate. Okay, so when we multiplied this by 2, for some reason that is not, there we go. When we multiplied this number of moles by 2, we got 0.020974 moles of zinc that we needed to use, and twice that was 1.37. Now you'll notice that I used the top loader here because this did not have to be super precise. So I just 1.37 grams went into the soup, and slowly but surely the soup stopped being blue, because the blue is copper 2+. The blue is copper 2+. So as copper 2+ was there with zinc, and zinc was reducing it to copper metal, and zinc was being oxidized to zinc 2+, the color was going away. Okay, the copper 2+ is blue. All right, so once all the color had gone away, and once all the fizzing had stopped, and you couldn't see any more of the gritty little grains of zinc around anywhere, it was time to clean this up and mass it and find out how much copper we had made. So this was our mass of the copper and the container, and this was the mass of just the container. That doesn't look like there's a whole lot of copper there. And in fact, there isn't. We only managed to get 0.7401 grams of copper out. Now, what's this all about? Well, you know how to find the the molar mass of copper, sorry. So it was just 0.7401 grams of copper times times 1 mole over 63.55 grams, and that gave me that number of moles right there. Okay, so that's good. We know how much we actually made. We know that this is our actual yield. Good. But now we're going to do some more stoichiometry. We want to find out the theoretical yield of copper based on our copper tetraamine. So based way back here on this blue guy, so I'm going to change ink colors. So from here, okay, and the theoretical yield of copper based on copper sulfate pentahydrate. So let's change to gray. From here. All right, so we were doing stoichiometry to find the copper from the copper sulfate pentahydrate. And here we were doing the stoichiometry, the manipulations to find the theoretical yield of copper from the copper tetraamine complex. So let's go ahead and give this a shot. Here is our theoretical yield in grams of copper. That's what we're going for based on the starting mass of copper tetraamine. And you know what? I already know this number. Not only that, I got that a few slides up, but that was 0.019556 moles of copper number 1, right? Copper tetramine complex. And remember, we said all of our molar ratios were 1 to 1. So 1 mole of copper metal to 1 mole of copper number 1, or tetramine. These cancel. And we end up with the same number of moles, again, of copper that we had of copper tetramine. So that would give us this number right here. But that's not all we want. We want the theoretical yield in grams. So we need to take that 0.019556 moles of copper and multiply it by copper's molar mass, 63.55 grams per mole. And when we do that, we're going to find the actual grams of copper. So we should have gotten, based on the amount of copper tetramine that we got, we should have ended up with 1.2428 grams of copper. So that's what's right here. That's what we should have gotten. Okay, so let's see, what's the next question in our calculations? Now that we know the theoretical yield of copper based on copper number 1, we want to know the percent yield, which, remember, again, is actual divided by theoretical times 100. Our actual was right here above it, 0.7401. That's all the grams of copper we got, divided by what we should have gotten, 1.2428 grams, times 100%. And this would give us 59.55%. 4 sig figs, 4 sig figs. All right, so that was based on the copper tetramine, close to back at the beginning. Now we want to know the theoretical yield in grams of copper based on the copper number 2, the copper sulfate pentahydrate. So again, rather than starting from scratch, I'm going to come here and find, here was my copper 2-sulfate pentahydrate, and here were my number of moles. So I'm going to start with that. So 0.010487 moles of copper sulfate pentahydrate. And we had, again, a 1-to-1 ratio, molar ratio. So that gave us 0.010487 moles of copper. And now I want the theoretical yield in grams. So 0.010487 grams of moles of copper times copper's molar mass, which is 63.55 grams per mole. And we ended up getting 0.66645. 5 significant figures. Well, we can round it to just 5 because I only had 4 there. Grams. And that's my theoretical yield from copper sulfate pentahydrate. So the very last question, oh my gosh, we're almost done. The very last question is to find the percent. Come on. To find the percent yield. And the percent yield again is actual divided by theoretical times 100. Our actual was 0.7401 grams. Our theoretical was 0.6665 grams times 100%, or, that doesn't look right. 111.05%, or 111.1%. Now, how is that even possible? I mean, okay, the first one, that 59.55% isn't great, but at least it's understandable. But this 111, how can you get more than 100% yield? Well, I want you to think especially about the last couple steps. You have your mass, your copper 2-sulfate pentahydrate. You've dried it, you've masked it, you've dissolved it in water, and what did you add to it then? You added zinc and sulfuric acid, and I just described to you why. After the solution was no longer blue, we kept bubbling and boiling it. Why? Because there was something still in there. What was in there? Yeah, exactly. I'm not telling you. You're going to have to figure it out. There was something still in there, and we were trying to destroy it. What happens if we never did destroy all of it? Okay, there's one possibility for a screw up. Another one. This stuff is wet, right? We make the copper. It's soaking, dripping wet. So we put it in the Buchner funnel, we pour over some methanol, and we pour over some acetone, and we pull on it for a while, and now it's light and fluffy and dry. Really? Maybe? Maybe not so much? That's another possibility for an error. As you think about sources of error, reasons why things are not 100%, you need to actually think about what in the chemistry or what in the actual procedure could have happened to change the result. If you ever write down human error for a reason that something's off, I will give you no points for that question. If you ever wrote down because my calculations were wrong, I might even take off more points than it was worth to begin with. I want you to think about what in the procedure or what in your actual lab experiment itself or what in the chemistry could cause something to turn out not quite the way you thought it should. Okay? So anyway, give it some thought on this. Next week we'll have kind of a fun lab that has no math involved in it practically, so you'll be glad to get back to that. If you have any questions on this video or on anything I've explained to you, just shoot me an email, and we'll talk to you next time.